In this lecture, I'm going to provide an introduction to multiple regression analysis, and I'm going to do so by reviewing regression analysis from a single predictor perspective. And so when we think about trying to predict y from x, another term for regression analysis is test of independence, and it's assessing the independence across the different levels of the predictor variable and its resulting prediction of y. So really what we're looking at here is whether the population average of y is identical at each value along the predictor variable along the x-axis here. And this is what's referred to as a conditional distribution. So if we take a look at this graph, here we have our independent or our predictor variable along the x-axis, and I'm just going to highlight three different values along this x continuum, and we ask the question, can these predict the outcome along the y-axis or the criterion variable? And so what we see here is that at each of these levels of the predictor variable, the outcome data forms or at least we assume forms a normal distribution, and we have that here. And this is one of the assumptions of conducting a regression analysis, is that the predicted value of the data will form an approximate normal distribution along each value of x. And so the test of independence is essentially evaluating if the average value of y at each value of x is different along each value of x. So the expected E for expected value of y, does this equal alpha for all of the x values of our predictor variable, where alpha is actually equal to, is the y-intercept. Alpha is equal to the average along all of these, along the full continuum of x. So what we would see in this hypothetical is that along each value of x there is no independence, since all the values are equal to each other, those values being the mean of the data distribution of y at each of these values of x. And regression analysis is all designed to evaluating if the values along the predictor variable are independent of each other, and that we clearly see that they are not independent in this hypothetical scenario. From a statistical perspective, the test of independence or regression analysis, once again here, we're just going to focus on a single predictor model that it follows the inferential testing approach, where we state a null hypothesis and a competing alternative hypothesis. So the null hypothesis for this test of independence is that the beta will equal 0, beta being the slope of the regression line when we just have a single predictor. If that slope is 0, we're looking at a horizontal line, as we saw on slide number 2. If the line is not horizontal, then we would opt to consider the alternative hypothesis that it's not 0. And so this assessment of the alternative hypothesis that the slope is not 0, we adopt a two-tailed approach, and we don't assume directionality, and that gives us the option to consider slopes that are positive or a slope that could be negative. Now, these are outcomes that are conveyed on a computer analysis of a regression analysis. So here the key test statistic is a t-statistic, and the equation for the t-statistic is that the b is the slope of the line from the real data whereas the beta represents the slope, the hypothetical slope of the population. So if we set that slope to 0, and we divide that by the standard error, and we'll take a look at that equation here shortly, then our t-statistic simplifies to the observed slope of the data divided by the standard error of those data. So the b here, once again, is the sample slope. The degrees of freedom that we'll see here in getting to our calculation of the standard error is the sample size, n minus 2. And the SE is the standard error of the estimate for the slope. And to find that standard error of the estimate first requires us to find the standard deviation of the conditional distributions of y. And we extract data from a computer printout where we get the sum of squares error term, and we divide that by the degrees of freedom, which is n minus 2, compute the square root of that, and then we use that value in the determination of the standard error, where the denominator is just simply the sum of squares of the x value about the mean and taken to the square root. Now b is, as you can see here, b will be, the magnitude of b will be inversely related to the standard error. So in other words, as the sample size goes up, the sum of squares of x will also go up in the denominator, and therefore the standard error value, the quotient, will go down. So as we saw with other statistical approaches, as sample size goes up, the variability, the statistical variability, will tend to decrease. And what is often recommended to be calculated is a confidence interval for the slope. So the slope is generated by oftentimes a computer printout, and that slope is used in a regression model or a regression equation, but it's very helpful to calculate the estimated confidence interval by taking the slope computed from the data and adding and subtracting a critical value of t, which will be dependent on the sample size, times the standard error. And that t value is taken from the t table. If this was based on a normal distribution and we get a z value at the 95% confidence level, that would be a value of 1.96. But that value doesn't always align when we have small sample sizes, smaller than infinite. One of the outputs of a regression analysis when it's conducted through a computer program is the ANOVA table. And so the ANOVA model is used to establish how much of the outcome is predicted by the prediction model and the error. And so what we see here is the total sum of squares, which is similar to what we have with the ANOVA approach to examining differences, except this time the total sum of squares is going to evaluate the observed value of y in your data, subtract the average of that y value, squared. All of those values are added up, and that gives the total sum of squares, which is going to be some combination of the model sum of squares. The model sum of squares is based upon the hypothetical prediction model of your experiment, and so that will be equal to y hat being the predicted value of y, subtract the average value of y, and that's done across all the observed values of x to predict a y value. Note, y hat will not necessarily equal to the yi value. So the yi value is the real data point. After running the ANOVA model, the yi hat is the predicted value of y, and these two will very rarely, if at all, equal. An important component to the regression model is the residual term, or the error term, and that is going to be the difference between the actual observed data in hand as part of the experiment, subtract the predicted value. If the sum of all of these for each data point is really small, then you have a model that will have a very high predictive power of the data that you have. But oftentimes, the residual error is so large that it sort of overwhelms, if you will, the total sum of squares and the model sum of squares. And so the total will actually be more balanced towards the residual if the model is not very predictive. So what we see here, continuing with our ANOVA model, we have calculated what is essentially variances, that is a function of the total, or the total sum. The total variance in the prediction is going to be equal to the model variance and the error variance. So we just simply take these sums of squares and we divide them by the associated degrees of freedom. So the degrees of freedom for the total is just simply the sample size minus 1. The degree of freedom for the model is the number of predictors, and this value would be 2 if in a single predictor model. And then it's n minus k, where k is the number of coefficients, and that would be 2 if we have a single predictor model. And another way to express this equation is the variance of the total data is going to be some balance of the theoretical model and the actual error term, the difference between the observed value and the predicted value. And so we put a graphic of this here on the very bottom. We start at the top. So if we start with just one predictor, and so the expected value of y in our theoretical model for our population is going to be equal to alpha plus beta x, where alpha represents the y-intercept when x equals 0, and beta is the slope. Now in a multiple regression model, so this is our bivariate model. In our multiple regression model, as we see here at the bottom, we still have an alpha term. That's our y-intercept when all the x's are set to 0. But here we have more than one predictor. So with each predictor, we have an associated coefficient, which is the beta term, or the slope, associated with that one predictor variable. Beta 2 is the slope, or coefficient, for the second predictor. So this is not a second point along the x-axis. This is a completely separate and different variable entered into the analysis, and this continues for however many predictor variables one puts into their regression model. And these represent slopes associated with each of these two predictors. And just to review the theoretical model here, if we have our predictor, once again this is an illustration of a single predictor, we have we have the predictor variable along the x-axis, the criterion or our outcome variable along the y-axis, and we have a line that we would just describe as alpha plus beta x. This is our hypothetical or theoretical model for our population, where alpha represents the point of our y value when our x predictor value has a value of 0, where beta represents the slope of this line, assuming that it's linear. And if we just select a particular point on x, we go up to the line, the model should predict what our y value is. Now, this is theoretical, but in an actual regression analysis, we know that there's going to be scatter about this line. So a regression analysis will not only evaluate the predictive power of our model, but will take a realistic approach and factor in the reality that data does fluctuate about the line. So this ends this video, our first video here on multiple regression analysis.